Matrices belong to linear algebra. They are defined within a formal symbolic framework. The framework is abstract and internally consistent. A matrix is a structured collection of symbols. The symbols are arranged in a rectangular form. This arrangement follows a strict convention. The convention is assumed and not questioned. A matrix consists of rows and columns. Rows and columns define the internal structure. The structure is essential to the definition. It can be observed that order is fundamental. The position of each symbol matters. Symbols are not interchangeable without consequence. One may think of a matrix as an organized array. The organization is deliberate and fixed. It does not arise accidentally. The matrix exists as a single mathematical object. It is treated as a whole. Individual entries are secondary to the structure. The structure defines the matrix identity. A matrix is usually denoted by a capital letter. This notation is conventional. It does not affect the definition itself. The symbols inside the matrix are called entries. Entries may represent numbers or abstract elements. Their nature is not emphasized here. What matters is their placement. Placement is defined by row and column position. Each entry has a unique position. This position distinguishes it from others. The distinction is purely formal. It does not rely on interpretation. We may restate this description calmly. A matrix is a rectangular arrangement of elements. The arrangement follows strict positional rules. The rules are shared within algebraic practice. They remain stable across contexts. A matrix has a defined size. The size is determined by rows and columns. This size is called its dimension. Dimension is part of the formal description. It does not imply magnitude or scale. It only describes structure. The dimension must be specified. Without it, the matrix is undefined. The definition requires completeness. Completeness here means structural clarity. One may think of matrices as symbolic containers. The container metaphor is abstract. It does not suggest physical containment. The entries exist within the matrix formally. Their existence is relational. They are defined by position. Position defines identity within the matrix. It can be observed that matrices do not imply action. They are static objects. They do not change unless defined to change. Change is not assumed. At this stage, the matrix simply exists. The existence is symbolic and abstract. No operation is implied. No computation is required. The language describing matrices remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. We may remain with this definition quietly. A matrix is a structured rectangular array. This statement may be repeated. Repetition does not change meaning. The meaning remains stable. Structural properties describe how a matrix is organized. They do not describe action or operation. They describe form and internal arrangement. A matrix has a defined number of rows. A matrix also has a defined number of columns. These two quantities describe its structure. They are part of the formal definition. It can be observed that rows are ordered horizontally. Columns are ordered vertically within the matrix. This orientation is conventional and accepted. The convention is not debated or altered. Each row is distinct from other rows. Each column is distinct from other columns. Distinction is determined by position. Position is defined formally. It does not rely on interpretation. One may think of the matrix as a grid. The grid metaphor is abstract and restrained. It does not suggest physical layout. It only suggests relational order. The order of rows is significant. Changing the order changes the matrix. The same is true for columns. Order is therefore a defining property. It can be observed that entries are indexed. Indexing refers to row and column position. Each entry is identified by two positions. These positions are written symbolically. The notation follows established convention. Convention ensures consistency. Consistency reduces variation. Reduced variation supports predictability. The predictability remains constant throughout discussion. Matrices may be described by their dimensions. Dimension refers to the count of rows and columns. This count is part of structural description. It does not indicate value or size intuitively. It only indicates arrangement. A matrix with different dimensions is structurally different. Structural difference implies formal difference. The difference is not qualitative. It is purely symbolic. We may restate this description calmly. The structure of a matrix is defined by rows and columns. Rows and columns determine internal organization. Organization is fixed once defined. It does not change unless redefined. The matrix remains stable in structure. Stability is assumed, not emphasized. Matrices may be described using brackets. The brackets indicate grouping. Grouping shows that entries belong together. The brackets do not affect meaning. They are part of notation. Notation is a representational choice. The choice is standardized. Standardization supports shared understanding. Understanding here is formal, not intuitive. The structure of a matrix is independent of its entries. Different entries may share the same structure. Structure does not depend on values. It depends on arrangement. Arrangement defines the matrix type. Type here refers to structural category. The category is descriptive. It does not imply function. One may think of matrices as formally shaped objects. The shape is symbolic. It does not imply geometry. The shape refers to row and column count. This count remains constant for a given matrix. It can be observed that structural properties are static. They do not change during consideration. Change would require a different object. The discussion remains focused on definition. No operation is introduced. No computation is required. The language remains flat and repetitive. Sentences proceed evenly. No emphasis is introduced. We may remain within this structural description. A matrix is defined by its internal arrangement. The arrangement is given by rows and columns. This statement may be repeated. Repetition does not alter meaning. Meaning remains stable across restatement. Matrix equality is a formal concept within linear algebra. It is defined without reference to interpretation. Two matrices may be considered equal under specific conditions. These conditions are structural and symbolic. Equality does not depend on context. It depends only on formal properties. It can be observed that equal matrices share the same dimensions. The number of rows must be the same. The number of columns must also be the same. This requirement is assumed without emphasis. Without matching dimensions, equality is not defined. The definition requires structural compatibility. Compatibility here is purely formal. It does not involve meaning or application. One may think of matrix equality as strict sameness. The sameness applies to structure and entries. Each corresponding entry must be identical. Identity is determined symbolically. The position of each entry matters. Entries are compared by position. If positions differ, comparison is invalid. The comparison process is exact and rigid. There is no tolerance for variation. This rigidity defines formal equality. We may restate this idea calmly. Two matrices are equal if they match exactly. The match includes size and entry value. Criteria are introduced. The equality is absolute within the system. It can be observed that matrix equality is symmetric. If one matrix equals another, the reverse also holds. This symmetry is assumed as part of equality. It does not require separate justification. Equality is also reflexive. A matrix is equal to itself. This statement is formal and uneventful. It introduces no new structure. Equality is also transitive. These properties are accepted without emphasis. They are not explored in depth. Exploration would increase engagement. Engagement is not required here. The concept remains abstract and restrained. Matrix equality does not imply action. It does not suggest transformation. It simply states a condition. The condition exists independently of operations. Operations may be defined later. At this stage, equality stands alone. We may continue within this description. The entries of a matrix are elements. The nature of these elements is not central here. They may be numbers or abstract symbols. What matters is their exact correspondence. Correspondence is determined by position. Position is defined by row and column indices. Indices are part of notation. Notation follows standard conventions. The conventions are stable and repetitive. Repetition supports predictability. Predictability supports monotony. We may restate again using similar phrasing. Matrix equality requires identical structure and entries. Structure refers to dimensions. Entries refer to symbolic values. Both conditions must be satisfied. If either condition fails, equality does not hold. This rule is strict and unambiguous. Ambiguity is not permitted. The language describing equality remains flat. Sentences proceed slowly. No emphasis is placed on importance. We may now consider related conceptual properties. Matrices are distinct objects. Distinctness is defined formally. Two matrices with different entries are different. Two matrices with different dimensions are different. Difference is defined by inequality. Inequality is simply the absence of equality. It does not require separate structure. It is implied by the definition. One may think of matrix identity as precise. Precision is formal, not practical. It does not involve approximation. Approximation is not introduced. The concept remains exact. Exactness characterizes algebraic definitions. We may remain with this idea quietly. Matrix equality is a condition of exact correspondence. The correspondence is structural and symbolic. Matrices exist as formal objects within linear algebra. They are not defined by purpose or application. They are defined by structure and relation. The system in which matrices appear is symbolic. It is governed by convention and consistency. Matrices participate in this system as stable elements. They do not change meaning across contexts. Their identity is determined by structure and entries. It can be observed that matrices function as carriers of information. This description remains abstract and restrained. Information here refers to symbolic arrangement. It does not imply communication or interpretation. One may think of matrices as organized representations. The representation is formal rather than descriptive. It does not depict external objects. It only encodes relationships symbolically. Matrices allow algebraic systems to express relations compactly. Compactness is a structural feature. It is not emphasized as beneficial. The compact form is accepted as conventional. Matrices may represent collections of values. The collection is ordered. Order is determined by rows and columns. This order is essential to meaning. Meaning here is formal and internal. It does not depend on external reference. Matrices interact with other algebraic objects. The interaction follows defined rules. These rules are not discussed here. Their existence is assumed. Assumption supports continuity. Continuity supports monotony. We may restate this description slowly. Matrices serve as formal structures within algebra. They organize symbols according to position. Position determines relational meaning. Relational meaning is internal to the system. The system remains closed and self-contained. Matrices do not require interpretation to exist. They exist as symbolic entities. Their role is passive until operations are defined. At this stage, no operation is implied. The matrix remains static. Static objects support stable reasoning. Stability underlies algebraic structure. It can be observed that matrices unify multiple elements. The unification is formal. It does not suggest combination in a physical sense. The elements remain distinct within the matrix. Their distinction is preserved by position. Position ensures individuality. Individuality is symbolic. It does not imply identity beyond structure. Matrices may be compared to other algebraic objects. Such comparison is conceptual. Matrices differ from numbers and expressions. The difference lies in structure. Structure is multidimensional. This dimensionality is formal. It does not imply spatial interpretation. The matrix exists independently of visualization. Visualization is optional and not required. The definition remains symbolic. Matrices provide a framework for systematic representation. Systematic here means rule-governed. Rules govern structure and notation. Notation standardizes representation. Standardization supports shared understanding. Understanding remains formal and restrained. We may continue to restate these ideas. Matrices are structured symbolic objects. They exist within algebraic systems. They retain identity through structure and entries. They do not imply action. They do not imply result. They simply exist within the framework.